Good afternoon, guys. Today we are talking about friction. All mechanical systems undergo friction with the interaction of their members. At the end of this topic, you should be able to define friction, static friction, kinetic friction, coefficient of friction. You should be able to state the laws of friction. There are three of them. You should be able to perform numerical calculations from friction maximum condition. You should be able to realize that, okay, this is an induction for you in the development of the graduate attributes. One of the topics that will enable you to get inducted towards the development of your graduate attribute. Friction was ignored in our previous topic of dynamics when we started, just because we performed the analysis in the ideal condition to give you an overview of that. Now, to be realistic in the analysis, friction must be taken into account because no dynamics of mobiles and so on can take place without friction. The analysis of dynamic with friction is similar to the one without friction. The difference is only that friction here is taken into consideration. Friction is a force which opposes motion or which tends to oppose motion of one body relative to another through their surfaces of contact. Friction is a reactive force by nature. Two types of friction, three main types of friction can be highlighted: the dry friction, the rolling friction, and the fluid friction. And we are going to focus here on the dry static and dry kinetic or sliding friction. The example, one of the most obvious example is when you are pushing, for instance, a block from a heavy block on the floor. If you are pushing it, you will feel a resistance. Although despite the increase of the force you are applying, you will feel a resistance up to the point that suddenly that resistance will suddenly yield and the block will start sliding, moving, and with even a relatively smaller force, you should be able to move the block in that condition. In the diagram here shown, it describes you two main type of friction when we are dealing in the static and kinetic condition. We have a static friction and a kinetic friction. What is known as static friction here is a frictional force is a maximum friction force in the static condition, meaning in the condition when the object is at rest. So when you apply the force, the diagram here is made of the frictional force versus applied force. The applied force is performed and then there's a frictional resistance. As we said, that friction is the reactive force. So once you apply a certain amount, the object does not move, which means that friction brings the same amount of force to oppose. If you increase that force, friction will increase in the same amount because the object is still not moving. Until when you get to the amount of force that corresponds to the maximum frictional force. At that moment, if you go beyond that applied force, then friction will, the condition of rest will be disrupted. Therefore, the object will start undergoing a motion. At that moment now, the amount of frictional resistance will drop, also will decrease. So even with a relatively smaller force, you should be able to move that object. It means that friction has fallen from the static friction condition to the kinetic friction level. The coefficient of friction is a property of the two surfaces in contact with each other. So, okay, this coefficient vary from the surfaces of contact regarding the materials in contact, regarding the the type of the surfaces, the relative finish of the surfaces, whether they are rough or they are smooth. All these are factors that affect the friction coefficient. By definition, the friction coefficient is equal to the maximum static friction for the static friction coefficient over the normal reaction of the surface. Then the kinetic coefficient of kinetic friction is equal to the kinetic friction divided by the normal reaction of the surface. Now, since we just saw that the static friction is higher than the kinetic friction, subsequently it appears that the coefficient of static friction is greater than the coefficient of kinetic friction. The laws of friction state that the first law states that friction is practically independent of the contact area between the surfaces. This means that if you take one brick which has 3 different surfaces, let's take only 2 of the surfaces. Let's say one surface is 100 centimeters squared and the other surface is 50 centimeters squared, say. Then if that brick weighs, say 5 kg, if you lay that brick on the surface of 100 centimeters squared, it will give the same amount of friction resistance as if the brick is resting on the surface of 50 centimeters squared. So the friction coefficient the frictional resistance does not depend on the amount of surface area in contact. The second law of friction states friction is proportional to the normal reaction of the surface of contact, with normal pressure. Is what we just saw in the diagram there. So F friction is equal to mu friction multiplied by the normal reaction, the normal force. The third law states that kinetic friction is practically independent of the speeds, the relative speed of the 2 surfaces in contact. Meaning that if the one surface is sliding relative to the other, say at 2 meters per second, even if the speed increases at 3 or 4, the kinetic coefficient will stay the same, will stay unchanged. Now, in practical analysis, let's consider one scenario of a block sliding on a horizontal surface. The inventory of forces give in the normal direction to the surface, the weight going downward, and the normal reaction of the surface going upward. In the horizontal direction, it shows the driving force horizontal and the frictional resistance opposing it. So when we solve for the equilibrium along the normal direction, we'll find that the normal reaction Fn is equal to the weight, which is 490.5 Newton. If we solve in the horizontal direction, we'll find that the force net, which is the 200 minus the frictional force, must be equal to mass times acceleration, Newton's second law. Here, by resolving it and substituting the Fn into mu, we find that the acceleration is 1.057 meters per second squared. If you consider a second scenario where this time the object is still resting on the horizontal surface, but the applied force to move the object is lifted upward at an angle of 30 degrees from the horizontal. In that case now, the intensity of forces in the vertical direction will give Fn going upward, the weight going downward, and a component of that driving force, which is the driving force sine of the 30 degrees going upward also. In the horizontal direction, we'll have the component of the same driving force, which is horizontal, parallel to the surface, which is the 200 cos of the 30 degrees. Now, solving to get the normal reaction at the normal force, is not more equal to the weight, this time it is obtained by resolving for the equilibrium along the normal direction. In that, by resolving, you will find that some of the force going upward equals some of the forces going downward. Then the force going upward is the normal force, obviously, and the applied force sine of 30 degrees. Resolving it gives us, which must be equal to the weight going downward. Resolving that equation gives us the normal reaction equal to 390.5 Newton in our case. Now, in the same way, in the horizontal direction, the force net equals to mass times acceleration. The force net now is the 200 cos of 30 degrees. Mass times the mu Fn must be equal to mass times acceleration. Resolving it gives acceleration equals 1.121 meter per second squared, slightly greater than the case of the force pulling horizontally. Here we can comment that this increase of acceleration is due to the relief that the driving force lifted is relieving the surface of contact from the normal pressure and then the normal reaction. Therefore, enable the object to accelerate a bit greater, although the fraction of a driving force was also lost here due to that lifting up, and the remaining one being now just 200, the cos of the cosine fraction of that force. Scenario 3 here gives us, if we apply the same 200 Newton with the block resting now on an incline, say of 30 degrees from the horizontal, we resolve still for the equilibrium along the normal surface and the equilibrium along the dynamic equilibrium along the incline, the parallel surface of the incline. This resolution will end up giving us the acceleration, which is minus 3.454 meter per second squared. This minus is just telling us that the object will not move at all, because this force of 200 Newton is too little to accelerate the block on that incline of 30 degrees. Therefore, let's try to increase our force to 400 Newton here. Then we'll still do the same analysis and we'll find that our acceleration will be 0.5456 meters per second squared. You can notice that even though we have doubled the applied force, the acceleration is still very little, because this time with the incline, the driving force is doing a work against the weight of the object through the gravity component that is resisting the motion here. So, although the amount resting on the surface is just a fraction of the weight. Thank you, guys. It's the end of the presentation.